Hey guys. Hey guys. How's it going?
Hey,
Uh hey Eylon, how's it going?
all right.
Uh sorry, can you guys hear me?
I can hear you.
Okay,
Can you
great.
hear
Yeah.
Yeah.
me?
Hi.
Sorry, I my Zoom subscription expired, so it was only gonna be an hour, so I had to like re-update it and it took a second. So sorry for the slow for it's usually usually we start 15 minutes for an AV check. But no worries. Good to go. I'll update the Luma and I'll put this in the chat. Um Gal, do you want to uh, present your slides? Just make sure all the AV works and everything. Is for
Yeah,
if you're planning to present slides, you don't have to. But if you're
yeah.
planning,
I am. You need to allow me to present slides.
I always forget this
I don't
part.
have permissions.
Sorry.
Yeah.
Yeah, 1 second. All right. Okay, try now.
Back. And you can hear me fine, right? Because I
Yep.
had problems with my microphone before.
Yeah,
Okay.
I can hear you. Eylon, can you hear Gal?
Yeah, I can hear you guys. You should update the Luma.
Yes, I will update the Luma right now. I just wanted to make
Mm.
sure we had you guys all
Uh,
set, and I'll post the link in the group as well
okay,
right
good.
now.
Can you see the slides? Everything?
I can see. Yep, looks great.
Yeah,
Okay. Great.
yeah. Thanks, Alex. Thanks.
Yeah, no sweat.
Thanks.
Sorry for the delay here. Looks
Oh
like we
no,
have
no problem.
nine. We have nine people who registered, and we'll probably have a couple more people end up kind of filtering in too. So this will be good. 1 second here. Let me just update this with the link. Okay. And yeah, so Eylon, you should have gotten an email now with the updated link, and I will put it in the zkStudyClub channel. Do this right now. All right, great. So we'll give it a couple minutes here. My experience in the past with this is that the first 10 or so minutes, people will filter in. And then we get started maybe 5 to 10 past, depending on when we have kind of a quorum. And we'll let you present this work. Gal, it's up to you if you want to take questions throughout. If you prefer to wait till the end, it's totally up to you. By the way, is Gal or Gal? Like, what's the right way to say it?
It's Gal,
Gal. Okay,
which
cool.
is sort of in the middle. Yeah.
Just wanted to make sure. I'm an American English speaker, which means I mispronounce almost everybody's name. So, but I for the purposes of the video or for the recording, I wanted to make sure I do it right. And by the way, we are currently, just so you guys know, we're already recording. I'll just edit out all this at the beginning, and then we'll start at the we'll start right basically like when I introduce you. And Eylon, and is it Eylon is the right way?
Yeah, that's close enough. That's fine. Like even people in Israel have a problem with my name. So like,
All right. I'm sure
but
you're just making me feel better with that comment, but I'll if you have a problem with Eylon, then just let me know now. But otherwise, I'll just Gal and Eylon, because you guys are the co-authors,
no,
right?
yeah,
And Alessandro. So I'll introduce you. The way it'll work is I'll introduce you guys at the beginning. Then I'll let you read the title and you can jump into it, and then you can just let the audience know if you want to take questions at the beginning, or sorry, throughout or at the end. And then I don't know if you have two screens or not, Gal, but if not, then I can read from the chat as questions come in.
Oh yeah,
yeah.
I
I think
only have one screen here.
Okay, great. So if you want, well, maybe just tell me now. If a question comes in the chat, do you want me to interrupt you I won't interrupt you in the middle of your sentence, but like at the next pause, or do you want to just wait and hold all those at the end?
No, I prefer to have questions in the middle. So if people aren't understanding, then I can react to that. And Eylon, also feel free to butt in as well if you want.
yeah, I think questions are welcome, and even if people just unmute themselves, that's best.
Great.
Yeah, I don't mind
Yeah.
if people unmute.
Okay, great.
Let me just say one thing before people join and we start. There is a non-negligible probability that there will be sirens here. We're in Israel located. In that case, I guess me and Gal will go, and we will come back like in 4 minutes. So just maybe be patient. If that happens, I hope it won't happen in the next hour.
Yeah, definitely. Well, I was actually just about to ask how you both are doing. I was assuming you both were in Israel currently, and thoughts and prayers for you and your families during this time.
Yeah, we're fine, we're safe, but it's a complicated situation, and
yes,
hope we'll see peace soon.
Yes, I think we all feel that way. Having spent personally some time in the Middle East with rockets over my head, I also wish that you don't have to experience that for too much longer. So,
yeah.
Cool. So we'll let people filter in here. We've got actually a pretty good group already. I'm just going to get a glass of water personally, and then I think probably in the next 1 to 2 minutes we can just get started.
Okay,
so
great.
Eylon, as you pointed out, if there's any kind of interruption, we'll just plan on what we'll give it. What do you think? What is a reasonable interval for you guys? Was it say 10 to 15, let's say 15 minutes? I'll just put everyone on break for 15 minutes. And we'll plan on.
Yeah, I think 15 is too much. I think between 5 and 10 is
okay.
Is fine. Yeah. So
we'll make the plan a 10-minute. We'll just say 10 minutes. We'll resume, and then if for whatever reason it exceeds 10 minutes, we'll reschedule and finish the talk at like next week or at a different time. And so that way you guys can complete the talk, and we'll continue the discussion. But that way you guys have the opportunity, obviously, to get to shelter if you need to.
Yeah, that sounds good.
Sound good? Okay, great. Okay, let me just get a drink of water, and then I think we can just kick off.
I'll get some water as well. Has it outside. Yeah.
All right. Okay. So like I said, we're already recording here. And so we'll just take a quick pause. I'm going to just introduce you guys. I'll introduce both of you. Gal, I know you're presenting, but I'll introduce both of you since you're both co-authors. And then we'll be off to it. So welcome everyone back to another edition of zkStudyClub. This week, we're very excited to have Gal and Eylon, co-authors on this paper, the title of which you see here. And they're going to be presenting this work today. Also, a co-author who's not here is Alessandro Chiesa, who's been a guest here before. But with that, welcome Gal and Eylon. We look forward to hearing more about this topic. Please take it away.
Thanks for having us here. So I'll be talking about IOPs with IOPs with inverse polynomial soundness error. And as Alex mentioned, this is joint work with Ale and with Eylon. So hopefully everyone here knows what PCPs are, but I will just reiterate. We have a verifier that wants to know the validity of some statement, here modeled as X belonging to some language, and a prover that knows the answer and wants to prove it to the verifier. Sends some very long message, possibly long message, and the verifier reads a few symbols from this message and should be convinced whether the statement is true or false. And generalization of this PCP system are IOPs, which are just the interactive generalization. So the verifier and the prover have some longer conversation, which the verifier sends a message and the prover answers with a PCP-like message, and so on. And at the end, the verifier reads a few symbols from each one of the prover's messages and decides whether to accept or reject based on that. I should have mentioned at the beginning of my talk, anyone feel free to stop me at any moment with questions. Just unmute and talk or write in the chat. Both are fine for me. Okay, so that's IOPs. So why are we interested in IOPs? Well, I guess I don't need to talk about this too much in this forum, but they're interesting both in theory and in practice. In theory, they're an interesting abstraction layer for a lot of theoretical cryptography and also practical cryptography. They've been used in theory for delegation of computation, for hardness of approximation, and in practice, they're used to handle the validity of transactions of worth billions of dollars. They're very important, both in theory and in practice. So let's just, because I'm going to talk about a lot about these objects, let's just go over all of the parameters that we care about for interactive oracle proofs for IOPs. So the main parameters are the number of rounds, which is the main difference between PCPs, because PCPs have only one round or no rounds, depending on how you want to define it. The length, which is the number of symbols in the proof, the alphabet size, which is the size of the proof alphabet. So every symbol has some size. The number of queries read by the verifier, and the soundness error, the probability of accepting a false statement. Okay. So I'm going to go quickly about some of the known landscape for results on PCPs and IOPs. This is very partial, but it's what's more relevant to this paper. So the first thing I want to talk about is the amazing PCP theorem, which is the first, or no, first, but like a very big, important theorem, saying that NP has a PCP with polynomial length, constant alphabet size, the verifier makes a constant number of queries, and the soundness error is some constant, say one half. So yeah, this is an amazing theory, but there are still things that we could improve. The first thing that we could improve from this these parameters is the proof length. So we want a linear length PCP if possible. So that means that this poly-n turns into O of n, and the rest of the parameters are the same. And while we don't know how to do this for PCPs, we do know how to do it for IOPs. One of the main benefits of IOPs are improving the length of PCPs. The best PCP that we know is quasi-linear, so we're actually quite close in some sense for PCPs in this problem. Another problem that another thing that we could want to improve on the PCP theorem is this soundness error. So in real world scenarios, we don't want constant soundness error. We don't want the verifier to accept a false statement with 1/2 probability. That doesn't that wouldn't satisfy any customers. It wouldn't satisfy anyone. So we want to improve that. One way of doing it is taking the PCP theorem and amplifying. Here, I'm talking about soundness error that's inverse polynomial, which is a very interesting parameter regime. Which this is going to be the parameter regime that we're going to care about. If you want some other security parameter, you can take this and keep amplifying to some 2 to the minus lambda. But so if you take the PCP theorem and you amplify, that is, repeat the PCP logarithmic number of times, you'll get the soundness error that we want, so inverse polynomial, but you'll get logarithmic number of queries. And that's very costly for us, especially when thinking of how we take these PCPs or IOPs and transform them into real world systems, into snargs and snarks. This is very inefficient. And it's conjectured that we can actually get this by, instead of having a logarithmic number of queries, having a polynomial size alphabet, but still a constant number of queries. So we're reading more symbols, reading basically log n symbols, like bits, sorry, for every query that we make. But these are grouped together rather than in the amplified PCP theorem where they can be scattered apart. And this is way more efficient when we try to compile this into a snark. And
Can
also,
I
yes,
ask a
sorry.
question about the
Yes.
soundness error? So it says 1/n there. Usually I'd expect something like 2 to the minus lambda for a separate security parameter lambda. What's the relation between those two?
Sorry, what do you mean?
Why does it say 1/n instead of 2 to the minus lambda for some separate security parameter?
Oh, so here I'm talking about getting 1/n, and then if you want something better than that, you could improve it.
I see.
So specifically for the sliding scale, you wouldn't expect for this sliding scale conjecture, you wouldn't expect to get better. I guess in both cases for lambda, you would have some dependency on lambda. This would be the best dependency on n that we can have.
I see.
Yeah, so this would be the best that we could hope for, and then beyond that, yes, of course, you'd need some further amplification if you want negligible soundness error. But this would still be more efficient than taking the PCP theorem and then doing that. So the sliding scale conjecture, as you can see by this question mark, is unknown both for PCPs and IOPs. It's very important, like I said, for practice, but also for theory. If we get the sliding scale conjecture for PCPs, this has a lot of theoretical. This will give us a lot of theoretical results about hardness of approximation mostly, and also for if we get the sliding scale conjecture for IOPs, then by a previous paper of mine, Eylon and Alessandro and Ame, we know that this would imply with certain parameters, an IOP with these parameters, with a certain number of rounds, sorry, an IOP with these parameters would also imply the PCP theorem, so the PCP style sliding scale conjecture, sorry. And so this would also be a very important theoretical result. So both for PCPs and IOPs, it's very interesting. And the best PCP that we know, or the best that we know before this work, is by Dinur, Harsha, and Kindler, who get the 1/n soundness error, but they have a polylog n query complexity. So they don't, it seems quite close, but the gap is actually quite big between this polylog n and O of 1. Before I go to our result, are there any questions about this table? Okay, so our result is an IOP that is basically the best beats DHK and is yeah. So I'll just go over it. So we show that IOPs are beneficial for high soundness and small query complexity. Specifically, we show that every language in NP has an IOP with the soundness error that we wanted, 1/n, and has both round complexity and query complexity log n, or O of log n. So before we had polylog n, or if we just took the PCP theorem, just log n, and we get log n. More specifically, if we look at R1CS, then we can have a slightly better trade-off between the soundness, the alphabet size, and the proof length. So before I just wrote, general poly n here, but we actually get something that's relatively short as well. We not super short. We wish we could. We hope to improve that, but it's also quite short. Are there any questions about these main results? Okay. So the main tool to the underlying our result is a new test for Reed-Solomon codes. So first of all, what is the Reed-Solomon code? So Reed-Solomon code with some field F, some evaluation domain L, and degree D are all of the functions from L to D, such that there exists some polynomial of degree at most sorry, L to F, that there exists a polynomial of degree at most D that agrees with the function on every point. So it's basically the evaluation of polynomials over this evaluation domain L, of degree D polynomials, degree at most D, polynomials over L. The rate of this code is, which we'll denote by rho, is D plus 1 over the size of the evaluation domain. And we were in a test, for a proximity test for Reed-Solomon code. We have some function in the sky, f, that maps from L to the side, to the field. And we want to know whether it's actually a code word or something that's relatively far from a code word. So delta far from a code word. And the way that the approver is going to prove to the verifier this is using basically an IOP. So they have some interaction between each other. The verifier is going to read some symbols from the approver's messages and read some symbols from the function in the sky and decide whether it's it's convinced that it's a code word, or if it rejects it. And we require that if it's very far from a code word, then it should reject with some high probability. Yeah, this is what I've said. If f is delta far from the Reed-Solomon code, then the verifier should accept with probability roughly proportional to delta, to 1 minus delta. Because if we only change one symbol from f, from being a real code word, then the verifier is very unlikely to see this. So we can't expect to get very good to the verifier to reject with high probability. So what is known for these kinds of proximity tests? Well, first of all, there's a very long line of work on trying to do this with PCPs. I'm not going to cite all of them because there's really a lot of things. Altogether, they achieve a quasi-linear length, constant query complexity, but they have constant soundness error. So it only works if delta is if the code word is very far from low degree, which by far from low degree I mean far from the Reed-Solomon code, then it still accepts with some constant probability. It's not going to be sufficient for us. For our IOPs, we know something a lot better. So the most famous protocol by now is Fry. Fry has linear length, has log D queries and log D rounds, and the soundness error scales roughly with 1 minus delta plus some parameters that depend on the rate and on some small error. And our new proximity test for Reed-Solomon codes has slightly longer length than Fry, but has log D query complexity and round complexity. The soundness error is also very similar. This 1/4 parameter in the rate rather than 1/2 here, we can get rid of that. We know by now how to get rid of that. So you can just think of them as basically having the same soundness error.
I'll just say a small comment. In Fry, usually we think of the conjectured regime of parameters. If you assume this conjecture, then the square root rho in Fry is just square root, is just rho. And this is the same case in our result.
Yeah, I'll reiterate what Eylon said. For Fry, usually we think of a conjecture which says that this error is actually 1 minus delta plus rho plus some epsilon 0. This, what I wrote here is with square root rho is what we can provably show. And the same goes for us. We have a very similar conjecture to theirs, basically the same thing, allows us to get to the 1 minus delta plus rho. Are there any questions? Okay. So our protocol at a very high level has 2 different parts. Polynomial IOP for low degree testing and a compiler that takes polynomial IOPs and low degree tests and outputs proper IOP. So first of all, what are polynomial IOPs? I'm guessing that everyone here knows, but I will tell you again. So in a polynomial IOP, it's a restricted form of IOP, restricted for the prover, because all that it can do is send actual polynomials of degree at most some parameter d. So every one of the prover's messages is promised to be a proper polynomial over the entire field. And then the verifier can query these polynomials at whatever points it wants. So that's a polynomial IOP. And what we do is we build our low degree test in a recursive manner. First of all, we build a polynomial IOP that checks proximity for degree d polynomials. So it's a proximity test in the polynomial IOP model. In this polynomial IOP model, the prover is only allowed to send polynomials of degree at most square root d. So the prover sends polynomials of degree square root d, but somehow you're verifying a polynomial of degree d. We take this with a low degree test that works for square root d, for polynomials of degree square root d. The compiler takes these two things together and outputs a low degree test for degree d. So just to reiterate, we take a polynomial IOP where the prover uses degree square root d polynomials that allows for checking polynomials degree d. We take it with a low degree test for square root d, and we compile them together to get to d. And so we start with some arbitrary small value, let's say 2 in this example. So we have a trivial test for constant, for constant degrees, and this would be this, and then we compile this over and over again, growing the degree every time until we get to d. And because we square it every time, this takes log d steps. So each one of these compilation steps is actually going to be some constant number of rounds and some constant queries. And overall, we're going to get log d. So I will say just a few words about the compiler. We build a compiler for high soundness compiler for polynomial IOPs. It takes a polynomial IOP where the prover uses degree d. Before this was square root d. Here this is more general, so just d. A low degree test for degree d, and some rate parameter rho for the rate that the compiler is going to use, and it outputs a standard IOP for the same relation that the polynomial IOP was for. And importantly, we wanted to preserve high soundness. So if our compiler has the property that if the polynomial IOP has some soundness error beta, usually polynomial IOPs have very good soundness error, since the prover has way less things that it could do. So we think of this beta as something very small. And the low degree test has some soundness error epsilon of delta, where delta is the distance that that is promised, that we have to decide whether either the function is a code word or it's delta far from a code word. And the compiler outputs an IOP with soundness error. It's the maximum between this beta, which, like I said, we think of as very small, and the error of the low degree test when applied to just think of this as very large distance. It's very close to 1, depending on the rate, plus some small soundness error, but some small error. And this is important because of our the recursive way that we work. We have to keep the soundness error very high all the time. So the previous polynomial IOP plus low degree test compilers achieve constant soundness error, and so you would have something like epsilon of some constant here. And also importantly, because of this recursive construction that we have, the compiler invokes the low degree test only once. So remember, we built the low degree test using the compiler and low degree test in the previous rounds. So we can't have many calls to the low degree test because that would blow up very quickly. So we have to have only one call as well.
And one comment under the conjectured phi, then this would be epsilon of distance 1 minus rho and not square root rho.
Yes.
Or very close to minus 1 minus rho.
Yeah, it's 1 minus rho plus some very small value. Yeah.
Is it exactly the same conjecture that's used in phi, or is it just a similar conjecture?
I think it's very similar. I'm not sure if it's exactly the same one. I have to think about that. Eylon, are you?
We can come back to this.
I think it's at least very similar.
Okay.
Basically, it's basically going to be the same, but
I guess that yeah. So Gal will soon get to this proximity gaps and stuff like that. And we use we prove like a stronger version of what's known about the proximity gaps. And so then if you have the conjecture, oh, you need a stronger version also to this conjecture.
I will also, sorry.
Yeah, so currently I don't think it's like exactly the same conjecture, okay? But I think soon we'll be able to prove that like these two things are if and only if.
Okay, thank you.
I will also mention that, yeah, sorry, Eylon. I will also mention that in this paper, we don't have this conjecture. This is this improvement with the conjecture is something in things we're working on now. So if you look at a paper, it's not going to appear anywhere.
Understood.
Someone raised their hand before, I think. Okay, maybe it was a mistake. So I'll keep going. Okay, so we have this picture of how we construct our low degree test. And in this talk, I'm gonna only talk about how we build this polynomial IOP for testing degree D polynomials. Sorry. Yes. Okay, so remember we have this function mapping from the evaluation domain L to the field. And we want that if F is delta far from the Reed-Solomon code, then the verifier should accept with probability roughly 1 minus delta. So if the delta is small, then it should still accept with relatively high probability. But what's more interesting is if delta is large, then the verifier should accept with very small probability. If delta is something like 1 minus 1 over n, the verifier should accept with probability roughly 1 over n. So we're going to have some assumptions on this evaluation domain. I will mention that this is similar to the assumption that Frey uses. So we're going to assume that the evaluation domain is a multiplicative subgroup of F star, whose order is divisible by some m, which you can think of m as roughly square root d. So in general, I will be omitting a lot of like floors, ceilings, plus minus ones. They just overcomplicate everything. So m is roughly square root d. So if things don't work out exactly, that's why. It's because I'm just omitting things. And the full protocol actually works where the evaluation domain is anything as long as F star contains a subgroup of the similar order. But here, for simplicity, we're just assuming that L is this multiplicative subgroup. So we're going to partition the evaluation domain L using a polynomial G. In general, I will use hat to denote polynomials. So G hat is the polynomial. So G hat of x is equal to x to the power of m. And why do I say this partitions? So we can think of all of the outputs of this polynomial when given values from L. and then think of all of the values that map to each one of these. And because of this multiplicative structure that we have, and because the subgroup order is divisible by M, this partitions L into partitions L into L over square root D, or L over M, different parts, which are all have the same size. I wrote here square root D again. It's actually sort of like M, I think. So we're partitioning it. I haven't explained why yet. So now for the why. We're going to use this fact that was, at least in this context, shown by Benson Sudan. And it's as follows. Let's take some univariate polynomial f hat. Then there exists a unique bivariate polynomial q hat. There exists a unique bivariate polynomial q hat whose degree in its first value variable is the degree of f over the degree of g. And the degree in the second variable is at most the degree of g, such that basically q hat encodes f in some of its locations. Specifically, q hat of g hat of z, comma z is equal to f of z for every z. Sorry, for every z in this evaluation domain. So in the evaluation domain, in this specific structure, q hat encodes f hat. And importantly, again, q hat has degrees that are relatively small, specifically in our case, because g hat has degree m, which is roughly square root d. These the degree took on the x variable and on the y variable of q is going to be roughly square root d. So we took a univariate polynomial of degree d and we turned it into a bivariate polynomial with degree square root d in both sides, in both dimensions. The converse is also true. So for every q hat with the right individual degrees, if q hat is q hat has this encodes in this way g hat of g, so q hat of g of z comma z is delta far from f of z on the evaluation domain, then this means that f is delta far from degree d. Yeah. So now I wrote all of things, and it's possibly very unclear. So I have a pictorial, a picture of this. So we take f and we map it to q hat. Every one of these partitions that we had turns into a row of q hat, because these are exactly, the rows are exactly q of I comma x. Right, it was g of x comma x. So now it's whatever value I is the row. So we think about these partition parts as being in different rows. And the row degree of q is square root d, and the column degree is also roughly square root d. So now that we have this mapping, what can we do? Well, let's assume for a moment that somehow we can send bivariate polynomials of degree square root d in individual degrees square root d. Well, then it's actually quite easy to test whether f is close or far from low degree. The prover will send this polynomial, this bivariate polynomial, which is supposed to have this property, this mapping. And the verifier will choose a random location and check whether it agrees with this polynomial agrees with f, the function that we're trying to test. And for convenience for later, notice that choosing a random value in L, which is this whole thing, and then is equivalent to sampling a row and then sampling a column that is relevant to that part of the row. So which is this, sample a row from S. S is the list of the rows, and then sample from Li, which is whatever maps to this row I. So for convenience, I'm going to switch this, but it's exactly the same thing. Again, I don't know yet how we send Q hat, but let's run with it for now. So why does this work? Well, suppose that F is delta far from a Reed-Solomon code word. Then by the previous claim that we had in the previous slide, for every bivariate polynomial Q hat, F is delta far from Q hat of G hat of X comma X evaluated on L. And so because it's delta far, and the verifier is going to sample one of the locations in which it's different with probability delta. And so the verifier accepts with probability at most 1 minus delta. So if we could send this bivariate Q hat, we would be done, basically. This protocol would work. And the problem is, how do we do this? We can't just send this. Remember, we are in the polynomial IOP model. So this means that the prover is allowed to send, or actually has to send polynomials of degree square root d. But these are univariate polynomials. And here we want it to send a bivariate polynomial. So it's not clear how to do that. And this is what we're going to do now. So what we want to do now is to show how we can send Q hat, or approximately send Q hat. It's not going to be precisely committing to Q hat. So we have this, and we have the power to send univariate polynomials of degree square root d. And we have this bivariate thing, which is supposed to have both its rows are supposed to be of degree square root d, and its columns are supposed to be of degree square root d. So we might as well utilize this fact and send the rows at least send something that we can do. So we'll have the prover send each one of the rows as a polynomial. So remember, the row is supposed to be q of I comma x. So this is supposed to be a polynomial of degree square root d. So the prover can actually, the honest prover can send this. So we'll have the prover just send all of these. Okay. Well, we wanted a bivariate polynomial. So we have to test that these rows are actually consistent with some bivariate polynomial of individual degree square root d. We know that the rows of whatever I sent are degree square root d because we're in the polynomial IOP model. But what about the columns? What about looking at the rows one after the other at the same location? Why should this be the evaluation of degree square root d polynomial? And it should be that if Q hat was actually bivariate low degree. So our goal is to test that these columns are actually low degree. So the first thing I would do, I think the natural thing to do, is to choose a random column and try to test that it's actually of degree at most square root d, right? Because I wanted to test that these columns have some property. Might as well choose one and test this property. Okay. So how do we test this property? Well, first of all, let's sample a column at random. So CJ. And we want to test that it's low degree, that has degree at most square root d. And actually, usually this sort of seems like, we want to test something is low degree. And so now I sort of reduced it to testing that something is low degree. It doesn't seem to make sense. But the point is that CJ is supposed to have degree at most square root d. And because we're in the polynomial IOP model, it's quite easy to test distance from square root d. We have the prover send a polynomial that is supposed to just be the polynomial extension of CJ. It's just supposed to be the polynomial that agrees with CJ on all locations. And then if CJ is actually close to a low degree polynomial, there should be some V hat. So the verifier can sample a random location and just check whether V hat agrees with the column, which just means checking the row at the right place. So we just have the prover send a polynomial, and then we compare the column with the polynomial on a random location. So if this column is close to low degree, if it agrees with most of the points, then this test should pass with high probability, or conversely, if this was very far from low degree, then this test passes with very low probability because there is no degree square root d polynomial on which it agrees with a lot of points. Okay, great. So we've figured out how to do this test. But the question is, does this actually suffice? Is this enough? So Polyshuk and Spielmann showed in the 90s that if the verifier accepts basically this test, they showed a slightly different test, but it is implied from theirs that this would work. If the verifier accepts with some constant probability, some actually quite large constant, so like 9/10 or something like that, then there actually is a low degree bivariate polynomial Q hat, such that these rows are constant close to like they describe a bivariate polynomial that is constant close to this low degree Q hat. So that would mean that the prover actually sent something that is a constant close. But we wanted high soundness. We wanted the verifier. We don't want the verifier to accept with constant probability. We want the verifier to scale with the distance, basically. So it's actually still open whether in this test, if the verifier accepts with probably 1 minus delta for some other delta, say 1 over n, is it true that the rows are 1 over n close to Q hat? And we don't know. We worked quite hard on trying to figure this out, and we couldn't. So we have to find some other way to get around this. But it would be very interesting to solve this open problem, and it would possibly simplify the protocol. So the idea to solve this is to somehow test all of the columns at once. Because the reason that the Polyshuk-Spielmann doesn't work is that you're sort of limited to only one. You try to reconstruct things, and it just fails. So if you try to test all the columns at once, this should be much stronger. But the question is, how are we going to test that a lot of columns are low degree at the same time? This seems very inefficient. And this brings me to an interlude about proximity gaps. So we have a bunch of, think of these as the columns, but a bunch of claimed code words of the Reed-Solomon code. And we're going to take a random linear combination of them. So we're going to choose some alpha j's and generate some C star, which is the random linear combination of the CJs with so alpha j CJ. Okay. Why does this help us? Well, there's a nice theorem that says that if the probability that C star, this random linear combination, is close to Reed-Solomon code word, is with some relatively small probability, then actually all of the CJs are close to Reed-Solomon code words. So what this says is that if C star is close to Reed-Solomon code word on say these 3 green locations, then there are 3 green locations for every code word. So they're all actually close to low degree. And this tells us that in order to batch test C1 to CL, these columns, we can actually just test C star. We don't have to test all of them. And actually, the theorem that the authors here showed is much stronger than what I just presented. They show that C1 to CL have correlated agreement, which means that the picture is actually not like this. The picture is like this, where all of the code words have the agreement points are on the same location. So C1 to CL, they all agree. And in this example, on the last three locations. But notice that I drew it the way I drew it. C star has its three locations somewhere here at the top, and these have their location at the bottom. And this is actually a gap in this theorem. This theorem, actually, this is what they show. And you can conjecture that, or we conjecture that the picture shouldn't actually be like this. It should be like this. So the correlated agreement should also include C star. And if C star is close on these three locations, then they should all be close on these same locations. So they should all agree with each other. And this is so this seems very natural. It doesn't come out precisely from the at least not from the theorem. It probably does from the proof, but it would be nice to actually prove this conjecture. And in this talk, I'm going to use this conjecture. But in the actual paper, we bypass this conjecture by proving a weaker lemma that suffices for us. So again, what is the conjecture? I'm saying take a random linear combination and then test that it's close to low degree. And in the same points where it's actually close to low degree, then the columns or the code words that we summed together are close on these exact locations.
Gal, I'll stop you for a second. There's a
Yes.
question in the chat. Do you run, Pratyush asked, do you run batch try on multiple columns? So I think you're about to answer this. I'll just say that we don't run fry because fry is too expensive. So we cannot run fry. Like we're doing something more efficient than fry. We do batch these columns together, but Gal is going to present what is the problem with batching them in a second. And just a second comment that this conjecture is just for ease of this talk, like in the paper, we don't use this conjecture, and it's related, but has nothing to do with the conjecture on the parameters that you can get up to rho and not square root rho.
Yeah.
Okay. So that's like a conjecture of of list decoding. How close can you get to the rate? But because we need this exactly slightly stronger version that they didn't explicitly prove in the paper. So like now we have two conjectures for the parameters. We did open up the proof. It looks like you can prove this. It just, it takes a lot of time, and eventually we just change the protocol to get around this. Okay, but yeah, for this talk, it's much easier to just assume that this is true.
Yeah, for this talk, just assume it's true. Like Eylon said, it seems by going over the proof of this paper that it should be true, but proving it is this is a very complicated mathy paper. So proving it was it seemed like a lot of work. So we managed to get around that. Okay, so oops. Yes. Okay. So now that we know that we can, if we batch test, we can batch test all of the columns by testing the random linear combination. Let's try to do that. So the verifier will choose coefficients. And this, now that we have the coefficients, then this C star is just well defined by the sum, the random linear sum of these of the columns. And now we want to test that C star is low degree. And this goes to the question. So like, how do we test that C star is low degree? More precisely, how do we access C star, right? Because reading one location in C star, we have to read all of this sum. So that just means querying the entire row or every column and checking the sum, it doesn't make sense. This would have query complexity that's huge. But you should observe this following fact. So C star, by definition, C star at some location I is the sum over all the columns of alpha j, cj at location I. But what does it mean to sum all the columns? It means to sum over this row, right? Because each of the columns at a specific location is just the row, the row R at all of the each one of the column locations, right? And this looks like this row R is actually a polynomial. We know this because the prover sent it to us, and we're in the polynomial IOP model. And this looks like a weighted polynomial sum. This looks a lot like the sum check problem. So we want to check the sum of some polynomial over a bunch of locations. In this case, they're weighted as well, but whatever. So this is actually what we're going to do. So we're going to use a univariate sum check protocol. So in the univariate sum check problem, we have or the problem that univariate sum check solves, we have a univariate polynomial p hat and a multiplicative subgroup L, which was exactly the case that we have here. In this case, p hat was Ri. And we have a high soundness small query polynomial IOP to prove that the sum of p hat over the evaluation domain is equal to some gamma. That's what the univariate sum check does. And I will very quickly give some hints as to how this works. This is not a protocol we invented, but just if people probably here, most people have seen it, but it's surprising to people who haven't. So it uses these the following fact that if the degree of a polynomial p hat is smaller than the size of the summation domain here, this L here, then the sum actually reduces to the location, the zero location of the polynomial times the size of the summation domain. This is sort of because like you sum over roots of unity and you fold over things. And so it just suffices to query p hat at 0 in order to compute the sum. This is if the degree is small enough. But what happens if the degree is larger? Well, very roughly, we split up the polynomial into two parts. One that has small degree, and the other one that zeroes out on whose sum is 0 over the evaluation domain. This has something to do with the vanishing polynomial over this domain, but doesn't really matter. And so then the prover can send these two polynomials, and the verifier can sort of check consistency. At very, very high level, this is how the univariate sum check works. And like I said, here I was talking about regular univariate sum check, whereas we need a weighted version of that. But minor changes can get us to a weighted univariate sum check. So again, we wanted to basically access C star at a certain location, say I. And in order to do that, we noticed that the C star at I is just the sum of, or weighted sum of this polynomial. And so we use the univariate sum check in order to let the prover prove to us what the value is, rather than summing over everything. So I hope that answers the question of before. So no, we don't need to use Fry. We use a univariate sum check, which is very, very efficient. Okay, so now that we know how to access C star, we want to test that C star is low degree. So we're going to do the same strategy that we had before. We let the prover send the polynomial that is supposed to equal C star at all of these locations in S. So we send V hat. The verifier samples a random row and then checks that V hat and C star agree on this row, which again, to access C star, requires using the univariate sum check, and accessing v hat this is just a polynomial that is set by the prover. So the verifier has access to that. Yeah. Are there any questions about the protocol? Okay.
There's no more questions in the chat. So Gal, I think you can go ahead and proceed.
Okay, thanks. So just a sketch of the analysis. So if we look at all of the points in which C star agrees with V hat, so these are the locations in which C star is close to some specific low degree polynomial. Here they're marked in green. So by this proximity gaps conjecture, this means that for every CJ, there exists a low degree polynomial CJ which agrees CJ hat, sorry, which agrees on this exact list of points. So the picture is like this. So each one of the CJs separately is close to low degree on exactly the same points that C star is. And then we have to do some kind of interpolation to get out of this a low degree bivariate polynomial Q hat that agrees with all of these rows that are in green. So for every one of these rows in which C star agrees with V hat, this low degree bivariate polynomial will agree completely with the row. And so we've managed to send Q hat at least in these locations. I don't know what happens in the rest of the locations, but in the locations in which C star is close to V hat, we've managed to send Q hat. Yes, someone raised.
Yeah, you got a question. Pratish, you want to go ahead and just say your question?
Yeah. So my question is, could you quickly go over how you get the log n number on the complexity of this?
Here it's all so first of all, here we're still in the polynomial IOP model. So this is not an IOP. This is we're assuming that the prover can or has to send like actual polynomials in each one of its messages. So these R hat is an actual polynomial. This V hat is an actual polynomial. The reason that we get so here we have we're going to have constant query complexity, a constant number of rounds. So we have 4 rounds plus if I go here, sorry, skipping ahead just to go back to where we were. So we have some constant number of rounds. This is the protocol, the polynomial IOP altogether. I just went back to where we were at the start and put all this how do we send Q hat in this box. So hopefully that makes sense. So here we have a constant number of rounds, and the verifier only makes a constant number of queries. I didn't say this maybe, but a univariate sum check has a constant number of queries. And but this is only one round of our recursion. So here we're assuming that the prover sends polynomials of degree square root d, and we're showing how to verify polynomials of degree, or that code words that are supposed to be of degree d. And so if we start with some constant, say 2, and for 2 we have trivial low degree tests, this will give us 4, right? Because we have something for 2, and then the low degree test for 4, we can plug this in with the new another polynomial IOP for 16 and or for 8 and so on, right?
Can I ask you a question? What are you considering to be a unit time operation here? So if it's log d rounds.
So any field operation is a unit time for me.
Okay. Yep, got it.
Also, one quick thing here. You said the verifier. I see that the verifier communicates in a constant number of messages, but the messages themselves the coefficients, like they kind of do relate to like how many columns you have, perhaps, right? Because you're sending one alpha per column. So that doesn't seem constant, right? Or am I missing something?
This means that the verifier's running time is not going to be constant per round, or its message complexity is not going to be constant per round, but the number of queries that it makes is constant.
Sounds good.
So the number of symbols that it reads from the prover's messages is constant.
Let me just add a small comparison to phi. So in phi, you go from, in one like step of a recursion, you go from degree d to degree d over k. And you can set k to be whatever you want. You can even set k to be square root d. Okay, and then in phi, you would actually have log d rounds. However, in phi, you pay a factor of k. So you need to read things of size k. Okay, so that's why, like in practice, you can only set k to be like 8 or 16 or something like that. Here, we managed to go from degree d to degree square root d and only paying like a constant, like regardless of d.
Sorry, hopefully I answered the questions that were before.
You answered mine, yes.
Okay.
Yeah, I think we're good to go.
Okay. So again, we wanted the prover to send over q hat with this property, and then the verifier to check q hat at some location. And now we've shown how to, in the polynomial IOP model, how the prover can send or roughly send q hat. And this is exactly the protocol that we had before. Now I added it to the picture again. So we had this C star, we had this V hat, and we checked that they were that they agreed on some points. So now we know also that what the prover is going to do is send rows or Ri. So when the verifier wants to look at q hat at some location, it actually looks at the right row at the location of the column. And okay, there is one very small problem with this protocol. So far, actually, I haven't used in anything that I said, I haven't really used the conjecture. I haven't used the fact that
I was going to ask that.
Yes, that this green part here is the same locations as this part here, as in the C star area. I haven't used it. And the problem here is that what if I sample a location in this part 2 here? If I sample a location that is not part of this green zone. So I wanted to compare q hat, which is some low degree bivariate polynomial, with f, but I sampled outside of the low degree area, the area that I could actually prove that the rows sent by the prover are, agree with some bivariate polynomial. So in order to solve this problem, we can actually use the same I in this sub-protocol as in the outside protocol. So remember, I was the location that we're testing C star is close to V hat. So now the picture actually looks like this, because we're testing. So now I'm using the same I here as in here. The picture is like this because the location, if the verifier accepts, then this location must be part of this agreement domain of C star. Otherwise, the verifier would just reject, would just not agree with V hat. But because it agrees in this location, it must agree here as well. And therefore, we're actually, this part in this second part where the verifier checks agreement with F, it's actually in the area in which whatever the prover sent agrees with a bivariate polynomial. So this is where we're using this conjecture part from the proximity gaps. Like I think Eylon mentioned before, in the paper we don't use this conjecture, but we get around it in some other slightly using some slightly weaker theorem, but the conjecture we really believe it to be true. It should be true.
So for the verifier check to be sound, wasn't that depending on the fact that I was chosen randomly? Sorry, that J was chosen randomly? No, I think.
So yes, so it was dependent on both I and J, but notice that I here is chosen randomly. This is why I split it at the beginning.
Right, but
it's just easier here.
What I'm getting at is that are we assuming that the two choices of I are independent? Could there be some attack based on the fact that you've chosen the same I?
So there was an attack if it wasn't the same I. The fact that it's the same I sort of forces the prover to send things that are. I mean, this is part of the soundness of the security analysis. Let me think.
Okay, that's a good question. In general, making randomness is correlated is very dangerous. Okay, like that's a good strategy for an attacker. No, here it's not the case. We're choosing a random row, and then for this row, we're checking that the V is consistent with C star, and that this row is consistent at a random location with F. And so you conclude that you have, at least delta rows that satisfy these two properties. Okay, that's like if the verifier accepts with, some probability, then this fraction of the rows satisfies all the properties that you checked. And then from this.
Oh, right, because in the practical protocol, you'll be committing to these before choosing the random.
You're committing everything, before I.
Yeah.
Exactly.
Okay.
Yeah.
And so the prover can't cheat by changing the thing that was committed to. Okay.
Yeah. And then you take these rows that are close to F and close to V, and you know that they are close to F and they're close to a bivariate polynomial. So you can extract eventually a polynomial that is close to F from this. You extract a bivariate polynomial and then a univariate polynomial.
Yeah, the thing that was concerning me is that normally, say, using fiat Shamir, then all of the challenges have to be independent. I'd have to look at the proof.
Yep. Okay. So we have a short analysis, but basically it's just what Eylon just said. So I think I'm going to skip it. But it's basically just exactly what Eylon said. If you know that
just hold on that slide and no, carry on.
Just that if you have some delta fraction of rows, if the verifier accepts with probability 1 minus delta, then you know that you have a delta fraction of rows that, or 1 minus delta fraction of rows that has this property that is both agrees with T, with C star, C star agrees with V on these locations, and the location agrees the row. So the choice of the verifier agrees here as well. And so this means that there's a lot of rows in which you can, F agrees with some bivariate polynomial, and then you have to do some interpolation and you get univariate polynomial. And so you know that F is delta close to low degree. This is basically exactly what Eylon said, just with a bit more math.
Yeah, if you're thinking of fiat Shamir also, then you would need better soundness than this protocol. You need to amplify this. This means that you'll choose lambda rows and do this,
Right, I see.
Okay,
that makes sense.
The choice of the I1 up to I lambda, this is going to be independent.
Yeah, got it.
Yeah. And you also need to prove round-by-round soundness and not just soundness.
Yeah. Okay. So this concludes my talk. So to summarize, so we have high soundness IOP for NP with log n rounds and log n query complexity. So soundness error 1 over n and log n rounds in query complexity. We did this using a high soundness Reed-Solomon test, and it also required the development of high soundness polynomial IOP to IOP compiler. And if you think about it a little bit, you'll notice that actually what we did in the past few slides was a high soundness bivariate Reed-Muller test, actually. So we actually verified that we can verify bivariate polynomials, not just univariate. So we also get, for free, high soundness bivariate Reed-Muller test. For future work, there's a bunch of questions. So first of all, of course, what about practical implementations? This is all we did here was theoretical. So could this be efficient practically? How would this compare to Fry? Because we have significantly less rounds, but there's a lot of other things that are not efficient here. What about, we used bivariate polynomials very strongly here. What about more variables? Is that going to possibly buy us less rounds and less query complexity? There's improving this Polishuk-Spielmann lemma that I mentioned earlier about the simpler test that we had, that we didn't know how to get something better, but that would simplify this protocol. And proving the proximity gaps conjecture, we don't need it for this paper, but it just seems a bit absurd that that we don't have a proof for that. Like it seems like that should be true. Here
I contacted the authors of the proximity gap paper. They all said that it should be true, but writing a proof would take a lot of time. So yeah. I guess everybody's lazy. So.
Okay, and if anyone wants to know about how this compiler works, you can contact me or Eylon. I also have more slides about that if I don't know if anyone is very interested in this specifically. But yeah, that's it. And in general, I'm happy to answer any questions both now or later via email, whatever people want.
Awesome. Well, thank you, Gal and Eylon for presenting this. It was really interesting and sounds like a really great work on the theory side, and particularly hopefully will lead towards a lot of more practical breakthroughs on the ZK side and in other areas of cryptography. Before we conclude, I guess turn it back to the audience. Thank you for everyone who tuned in, by the way. We had a few people filtering in, a few people filtering out during the course of the talk, but for those that are here, do we have any remaining questions? We have a question from Pratyush. Do you have a sense of how much work it would take to generalize this to multivariate polynomials? So I guess it's actually just kind of asking about the difficulty of the second bullet for the future work heading.
So we've thought about it a bit. We have, I don't think we have any good ideas yet.
So that would be kind of replacing square root with kth root for a k variable.
Exactly.
Okay. Yeah, that would be replacing square root with kth root. Even so, on a theoretical level, replacing say square root with 1/3 is not super interesting, but for a practical case, it might be extremely interesting. So even improving from 2 to 3, like square root to 1/3.
Maybe I'll give us one comment about this.
Yes.
Yeah. So here we go from univariate to bivariate and then back to univariate. Okay, and we go from D to bivariate square root D and square root D, and then back to univariate square root D. Okay. Now suppose you go to a k-variate polynomial, then I think going from univariate to a k-variate polynomial of degree D to the 1 over k, I think that's like a reasonable thing, a little math, but that's not too bad. Then you want to go back from a k-variate polynomial to a univariate. Okay, that is more challenging. It's not that it's not possible. The question is, what is the cost of going from a k-variate back to univariate? Okay, you don't want this to be like higher cost than what you gained. And,
yeah. So for example, if k was 3, but that took more than was it log 2, 3 times the effort, then it wouldn't pay off. Is that right?
Yeah, so like one thing I know you can do, you can say, oh, let's take let's say a 3-variate polynomial, and then you do some reduction, you reduce it to a bivariate polynomial, and then you reduce it to a univariate polynomial. That would work, but then you have to compare, oh, why didn't I just do from univariate to bivariate, univariate, and then back to bivariate? So I got like a d to the 1/4 just with, 2 rounds of this. So it's like really in the details. And yeah, I do believe that maybe for practical reasons, maybe like 3-variate is like, a sweet trade-off.
I mean, it seems similar to the arity of a Merkle tree. For some hash functions, it works out as more efficient to use arity 3, and for some it doesn't.
Yeah.
So it would depend on the detail.
Yeah, I mean, it would also be interesting to directly, I know the multivariate polynomial low degree test, if you extend it to higher variables, I think the existing LDTs all have some shortcomings. So even without the application to univariate polynomials, maybe like if you can do something for like log n variate, like multilinear polynomials or something along those lines, would that be within reach or?
Yeah, then you go to log n, and the question is, what can you do with a log n variate polynomial? So I don't know the answer. This is something we're in general looking into, but yeah, I don't have like a good answer. Because you want to do something faster than log n, otherwise you would just run fry and that's it.
Yeah.
But yeah, potentially, yeah, maybe.
Yeah. So I presume this gives you like a Reed-Muller proximity. This will give you a Reed-Muller proximity test, right?
Yes. So currently we have just a bivariate, but we never worked on a general k-variate, but I believe that's possible. The question is only like, what is the payment as a function of k?
Yeah.
Yeah.
Is this the paper about the Polish-Spielmann lemma? The one I pasted into the chat?
Yeah, that's the Polish-Spielmann lemma.
Thanks.
Yeah. There's actually a version of Polish-Spielmann lemma for like the regimes we need here, but then they require like exponentially large fields and other stuff that are like, don't make them really useful.
Yeah, what practical size of fields would you use here? Because I know Fry can be used either on relatively small, say 64-bit, or large fields. Do you have any sense of which would be more efficient here?
I don't. Maybe Gal, you have an answer, but I think this is like any Fry-friendly field should be friendly here as well. It's like the same kind of algebra that's done on the fields.
Yeah, I agree. It probably should be the same. The errors are also relatively similar.
I see.
But again, this has no, like we didn't try in this paper to look at practical implementations, so it's very hard to know whether things like on a practical level, if they collapse, if it's better or worse than Fry, I don't know.
So what's your sense of how long it will take for someone to whether it's you or someone else to do the work of solving the engineering problems?
Yeah, so we are working on like a practical version. So we have like many improvements, practical like improvements. So this paper was more or less trying to go to solve the sliding scale conjecture, which is like a long-standing open conjecture. And on the way we're like realizing that, oh, this is actually like very practical. And so after we did that paper, we're working on like a variant on this that in terms of the O notation and everything, like doesn't change any of the results, but in practice, like shaves off a lot of things. Also, like in this paper, the verifier runs in like poly n time. Okay, like we didn't even, say anything, just poly n time. So of course we want to like polylog and time verifier and a very efficient one. Yeah. So we have like many improvements, but it's just the beginning. I think it will take some time until we have like something ready to publish.
Okay.
Yeah, I agree.
Sounds very encouraging. Yeah, it would be
yeah,
great
we
to have
encourage
a
people to take it and try to implement.
yeah. So I'm assuming that like Fry, this if it did result in a practical scheme, then it would be post-quantum secure.
Yeah,
Or
yeah,
could,
of
or
course.
could be.
Yeah, this is hash based, so
Yep.
just as secure as your hash function. Yeah, it's the same as Phi.
Right.
Internal that security. Yeah. And how much do you gain by loglog D? You know, it's hard to say. Depends on D. Sometimes log D and loglog D are roughly the difference between 4 and 5. So you don't always.
So that's interesting. Could you switch from one strategy to another if it turned out that the constants were such to make that a useful thing to do? So
you can do a lot of, yeah, like
use
actually
this for larger D and then go back to something
yeah, we were
else
initially
smaller D.
thinking maybe you do one round of our protocol, you reduce D to square root D, and then you just continue with Phi. Oh, and you can do all sorts. Actually, we think that the best thing is like some sort of combination of the two. But especially for large degrees, well, the trick is to gain, you know, the benefit. We have the benefits of Phi already, and we have the benefits of this. And the trick is to take like both and have something that is best. But especially for large values of D, and I think D is getting larger in time, right? Like we're seeing proofs to larger and larger computations. So I think especially for large values of D, like maybe 2 to the 25, 2 to the 30, then you should like feel the improvements of this protocol. Okay, like think of, you have 2 to the 30 in one step, like you go to 2 to the 15, which is like already quite small.
Yeah, yeah, understood.
Yeah, and then when it's smaller, like the Merkle paths are like, you know, you go from 2 to the 30 that has a Merkle path of length 30. In one step, you go to 2 to the 15 as the Merkle path in length 15. So the cost of the queries on the rest of the rounds are like negligible compared to the first round.
Yeah, it sounds as though you probably need at most 2 steps of this. Yeah, before it becomes very efficient.
So have you looked into like how to achieve negligible soundness error beyond just like naive parallel repetition? Because that seems like it would be problematic, right?
No, so okay, so if you want negligible soundness error, then you have to repeat the protocol, right, in some way. In Fry, this is very easy because you don't need to repeat the interaction. Like you don't do parallel repetition. You do the interaction phase once, and then you just tell the verifier, oh, you know, how many like things you want to open, and that amplifies the soundness. Here, the situation is slightly different because we have to choose which row to continue with during the protocol.
Right.
But if you know what soundness you want, like in the beginning, like, and you know what soundness you want, like that's the system. So you just know how many rows you want to choose, okay? And then you take these rows and you continue with them, and you take a random linear combination of them, and like you continue to the next round. So so in general, it's possible to amplify the soundness, and to make this amplification like very, very practical, that's not something we did in this paper, and that's something you should work out in a practical scheme.
So yeah, so in a practical scheme, if you committed to the rows and then you're taking a random linear combination, then that just becomes a random linear combination of commitments. Is that right? If you're using a homomorphic commitment scheme, okay.
Yeah, I don't know if you would get homomorphic schemes. If you wanted post-quantum, then that's more challenging.
Right. Yeah. Yeah. That's a good point.
Yeah, and also proving unbound soundness is slightly more trickier than here. But again, it's good to have trickier things in the proof and have a simple protocol.
I agree.
Awesome. Any final questions for Gal and Eylon? Okay. Well, awesome. Thank you guys. Thank you everyone for this great conversation, and thank you Gal and Eylon for presenting today. It was really great work. Thank you very much for being here, and hopefully we'll see you next time with for one of your future works, and maybe a continuation in solving some of these problems that you enumerated here. So thank you very much.
Thanks.
Thank you.